now East Coast. Okay, let me manage a little bit of things. And okay, cool. Hello, good morning and good afternoon and good evening. Once again, welcome you to this World River and Delta System Source to Sink webinar series. And so today we are very happy to invite Hannah Glover from University of Washington come here talk about Ayeyarwady River Delta, the tidal dominate, particularly in the channel sediment dynamic in Myanmar. So before I introduce Hannah, so once again, this Friday, Professor Andrea Augustine from the University of Washington also come here talk about tidal dominated river and estuary system. And she will cover a couple world major river system she has been working on. So Amazon, Mekong, Fly, Ayeyarwady, and maybe more. So please mark your calendar. Once again, because the both of them from Western Coast, apparently. So the time of the talk still 10 a.m. U.S. Eastern Coast. So that for them is 7 a.m. So please, and then we will return normal after that. Hannah is a graduate from New England Boarding College, and now is in the University of Washington. She got the master's degree there and still working on the PhD, but expected to defense next year. So she has been, I met her in Yangon, Myanmar, when she worked on the tidal channel, when we work on the shelf. So today she will present that kind of the teamwork of the tidal sediment dynamic. And so Hannah, now you can share your screen and put a presentation mode.
Great. Great. Thank you so much for inviting me. I feel very privileged to be one of the speakers in this wonderful seminar series. And I feel like, Paul, you've really done a service to our community in creating this sort of like permanent record of all these wonderful talks. So I'm gonna just jump right in and start. So today I'm gonna be talking very broadly about the Ayeyarwady River Delta. First over sort of kilometer scales, the distributaries as Paul introduced. And then I'm going to talk a little bit about some research we're doing on the smaller scale, meter to centimeter depositional processes in the lower delta that are really building the land surface. But before I dive in, I want to first thank our funding source, the Office of Naval Research, and all of our wonderful colleagues, Andrea Ogston, my advisor, and Chuck Neutrar, both of whom are here. As well as Aaron Fricke, who's a postdoc on this, and our colleagues from Myanmar, Cherry Ong Tet Nai from the University of Pathein, and Kyun Chu and Tai Tai from Myanmar Maritime University in Yangon. And I felt like I couldn't do this talk without at least sending out a little bit of love to our colleagues. We hope that they're okay. And we're really enjoying building these long-lasting connections, and we hope that we will be able to do that again in the future. I also want to acknowledge that I am giving this talk on the Indakina, which is the traditional ancestral homeland of the Abenaki, Pennacook, and Wabanaki peoples, past and present. And I acknowledge and honor with gratitude the land and the waterways and the Alnabak, or the people, who have stewarded Indakina throughout the generations. And with that, I'll get started just with a general outline for how this talk is going to go. So I'm first going to give just a little bit of background. There's been a very recent explosion of research on the Ayeyarwady River and surrounding area, so I'll just touch a little bit on some of those recent papers. And then I'll dive into the work we've been doing comparing distributary hydrodynamics and sediment dynamics and how that impacts sediment retention within the delta. And then finish with some new work that is not yet published that we're working on sediment delivery to the land surfaces in the lower delta. So I'll start with a figure that you probably, most of you are very familiar with. it ends up in many talks, just for a little bit of global context, because this is a global seminar series. So this is showing the sediment discharge to the coastal ocean by broad geographic region. And of course, we all know that there is this huge source here in, that's a coincidence of high elevation and high precipitation, where we have many of the world's largest river deltas. So just to highlight three that are in our study area, we have the Ganges-Brahmaputra, which is the second largest source of sediment, the Ayeyarwady, which is the third largest, and then the Mekong, which is the 11th largest. So these are really big systems and really fundamental to our understanding of nutrient budgets and processes, as well as being densely populated centers that are agriculturally valuable and economically valuable. So if you're interested, oops, sorry about that. If you're interested more in comparisons, I encourage you to tune in for Andrea's talk. She'll talk more about how these systems relate to each other, including the Fly River a little bit further south. But today I'm just going to focus in on the Ayeyarwady and do a deep dive on this single really fascinating delta. So just for a little bit of context, the Ayeyarwady River is almost entirely contained within the country of Myanmar. It flows out of the Himalayan syntaxis, like many of these large river systems, and then it enters the Gulf of Myanmar in the Bay of Bengal. And this region has a very important climate, the monsoon climate, that really ends up controlling a lot of the processes that I'm going to be talking about today. So I'm just going to introduce this concept, which you're probably, many of you, very, very familiar with, but just want to cover the basics so we're all on the same page, where during the southwest monsoon, humid air from the southwest brings heavy precipitation from June through October, and then that's followed by winds from the northeast that bring dry, hot weather and very little precipitation. And so if we look at discharge on the main stem of this river, which is in the Ayeyarwady, is measured at Pathein up here, pretty far above the delta. The discharge curve looks something like this, the annual hydrograph, where we have almost all of the discharge occurring during that southwest wet season, southwest monsoon. And this system, until relatively recently, was relatively unstudied because of Myanmar's political isolation. But there's been a lot of really wonderful research coming out. And there's a lot of reasons that we want to study this delta that are really sort of fundamental. So the first is that very little has been published on the system, and it's the third largest source of sediment. So that really increases our errors in estimates of global sediment, carbon, and nutrient budgets. So they're sort of really fundamental questions. But also the system is relatively unaltered by, and I emphasize relatively, it's relatively unaltered by damming, levee construction, or dredging compared to other megadeltas. So I'm not saying that it is unaltered, but it's relatively natural, which provides us a wonderful opportunity to connect morphology to sediment transport processes. And with that comes an opportunity to really look within a delta at intra-delta differences. So the largest deltas worldwide are tide dominated, including the Ayeyarwady, the Mekong, and the Ganges-Brahmaputra. Yet few studies compare distributaries within a delta. Most studies focus on a single distributary within a large delta system. And since the Ayeyarwady is relatively natural, we have this opportunity to really compare distributaries within the delta. So just to give you an idea of the research that's sort of bookending what my talk is going to be covering, there's been a fair bit of research both on the main stem and offshore. There are some great source to think talks, including by our own Paul Liu, but I'll start right at the upstream end. There's been a really great recent paper that has really nailed down the sediment and water discharge at Pathein. So we have these really nice hydrographs, and we have a really good idea of the sediment budget of the sediment entering the delta at the upstream end. And then we also are fortunate to have all this great research going on that is on the shelf, including Steve Keel and Paul Liu's recent papers. And I just want to emphasize for this this area of intense seabed mixing is going to come up again and again throughout this talk, where right in the upper Gulf of Myanmar, we have this area where there's a lot of sediment being moved about and continually resuspended by strong tides. And then on the sort of western portion of the delta, we have a lot less offshore sediment. So those are sort of the bookends for my talk. There's a lot of other research going on the Ayeyarwady, but those are sort of the two big highlights that I want to pinpoint. Because today I'm going to be focusing on what's happening really within the delta itself. So just to summarize once again, we have these two seasons, and we have a pretty good idea of this sediment coming into the delta, especially during the high flow season. And we have a pretty good idea, or at least we're getting a good picture of what's happening offshore, but we want to know what's happening really within the delta. So with that, I'm going to dive into the meat of the talk, which is comparing distributary hydrodynamics and sediment dynamics within the delta. And I'm just going to do a little shameless self-promotion that we recently published a paper on this, very exciting. So if you are interested or your interest is piqued in any portion of this talk, please do go check out the paper. There's even more detail there. So I'll start with a little bit of methods. We selected 3 distributaries to study for this intra-delta comparison. We selected the Pathein, the central Bogale, and the eastern Yangon distributaries. And these were specifically selected because they cover a wide range of conditions and sort of represent different ends of the delta spectrum. So the tidal range increases from 2.5 meters around the mouth of the Pathein to 6 meters at the mouth of the Yangon. There's really strong tidal amplification into the Gulf. But then the average seasonal wave energy increases in the opposite direction, where this western coastline is much more exposed to seasonal wind waves. And I'll talk about 3 different data sets that we collected in these 3 distributaries. The first is just we've deployed some fixed instruments to record the salinity, water level, and turbidity to just get a sort of baseline picture of what these systems look like. And then we conducted more intensive field surveys, both looking longitudinally along the distributaries and collecting 12.5-hour tidal-transect data at a single location where we went back and forth across the river to be able to calculate the sediment flux. So as I said before, we have these 2 dominant seasons, which is why we ended up doing multiple surveys. We really needed to capture both the high flow and the low flow seasons. And if we look at our fixed instrument data, which just gives us a nice idea of what the system is like, we can see these 2 seasons really clearly. I'm going to keep this map up here just as a little bit of a color reminder. I know that I'm going to throw a lot of place names at you, so hopefully that helps a little bit with orientation. So you can see that if we're just looking at the water level in the lower distributaries, these are tidally influenced regions. The tidal range is increasing from the Pathein to the Yangon. And then I'm going to skip over the story of suspended sediment concentration and come back to that in a little bit because it is very fascinating. I want to give it its due time and really focus on the salinity. So here in the lower delta, the distributaries are transitioning between estuaries, so there's tides and saltwater, to tidal rivers where there are tides, but there is no salt in the lower distributaries during the high flow season. We'll start by diving into the data that we collected during the high flow season when these are tidal rivers. So there's strong discharge from upstream that's really pushing that estuary further seaward. So just to introduce you to the next chunk of data, we collected these tidal transects during the high flow season, where we were at a single location in the river and we went back and forth collecting water velocity and suspended sediment concentration so that we could calculate the instantaneous sediment flux and then We do that over 12.5 hours so that we can then calculate the residual tidal sediment flux. I'll show that again later, but I just wanted to talk a little bit about, we had a lot of fun with our measurements here. We had to get pretty creative because we didn't have ADCPs that were hull mounted in any of our vessels. We're using vessels of opportunity, so we had to get pretty creative in how we installed our instrumentation. So sometimes we were towing an ADCP, sometimes we had this very official hull mounted ADCP strapped to the side with bamboo poles. And then here's our very fancy dry lab setup where we would be collecting data and quality checking. So I'm going to walk through in a lot of detail our tidal-transect survey from the Yangon distributary during high flow, just to give you an idea of what this data really looks like. And that'll set us up to talk about this in more detail. So just as an example, so we're in a tidal river, the water level is going up and down over the tide. And if we look at a specific point in the tide and put a transect of velocity across the river, that's what this would look like, where blue is seaward and red is landward. So this is during the turn of the tide. We can take that velocity and we can calculate the instantaneous water flux and sediment flux, which is what each of these points are. So that'd be a single transect across the river. And you can see that we have flow that's going both downstream and upstream. The tides are really strong here. It's a 6-meter tidal range. And we can integrate that over a full tidal cycle and calculate the residual sediment export or import, in this case, sediment export from this distributary. We can also look at other trends within the tidal cycle. So we can look at the bed shear stress and the average velocity over a tidal cycle. And what we see in the Yangon distributary during this high flow season is that the river is really a very powerful force that acts to oppose the tide. So during the ebb tide, when the river and the tides are acting together, we have really, really strong bed shear stress and velocity. But then when the tide is flooding and opposing the river discharge, we have very low, we have this minimum in velocity, and that lasts throughout the whole flood tide. So over that same time period, we're getting temporary sediment deposition as our velocity drops. And then right as the tide turns to ebb again, we get this peak in resuspension of sediment that's being repicked up off the bed and recycled, transported further downstream. And so that's a really detailed look into just the Yangon distributary during the high flow season. But we can see very similar trends in the other distributaries during this high flow season. The distributaries are relatively similar. So I'm just going to give you a brief summary in that the Yangon, Bogale, and Pathein distributaries are all tidal rivers exporting water and sediment to the Gulf. The Yangon was the largest distributary that we measured, and the Bogale was the smallest at just 5% of the total discharge at Pathein. And we estimate, just based on morphology, that we think the missing fraction is primarily discharged through these western distributaries. But in the future, we'd love to be able to go back and do some more research and look at some more distributaries. So this tidal transect data gives us an idea of the residual sediment export. And it also allows us to estimate how much sediment that's carried at Pathein is actually retained within the delta itself. So what fraction is not exported to the coastal environment. And we can do that really with a simple box model where we have sediment carried from the uplands. At the main stem, we have this great study from Varanasi at Pathein where we know pretty well what the sediment flux is. And then our study, we have tidal transects, which are here marked in yellow on this map. And so we can calculate how much of the sediment is retained in the upper delta by finding the difference between these values. And in this situation, I'm defining the upper delta really based on where we have data. So it's something that could be refined with future research, really sort of looking more longitudinally. But what we see is that somewhere between 20 and 60% of sediment from the main stem is retained within that upper delta during the high flow season. So that's really interesting and reinforces what we know about deltas, which is that they are very good at retaining sediment, and that the discharge measured at the main stem above the influence of tides is not representative of what's delivered to the ocean. So this sort of range is comparable to what we see in other large rivers like the Amazon, Mekong, and it once again really emphasizes that the main stem is not equivalent to what's delivered to the coastal ocean. So that was all from the high flow season when we have most of the discharge coming downriver. We see some really interesting things. Things get really fun when we look at this low flow season, when we're now dealing with estuarine conditions within the lower distributaries. And I'll just start with some looking just at the suspended sediment concentration or turbidity within the lower distributaries, because we see really stark differences. So here I'm just showing the high flow suspended sediment concentration probability distribution for the three distributaries. And you can see that they're all very similar. They're in a similar range, and turbidity is really being defined by that upstream river delivery. But if we look at the low flow season, we see this dramatic change in conditions where the Pathein distributary actually gets less turbid, the Bogale gets very slightly more turbid, and the Yangon gets dramatically more turbid to the point where it is almost consistently concentrations greater than 1 gram per liter, up to the maximum concentration was something around 13 grams per liter that we measured. So this is really chocolate melt conditions. It made it pretty hard to study because ADCPs were not designed to work in those types of conditions, but it's really fascinating. And it's not something we necessarily expected going into this, to see this dramatic difference in turbidity between three distributaries of the same system. So we wanted to understand what was driving this difference in processes. And so the first hypothesis is that perhaps there's a difference in the structure of the estuary. Perhaps there are stronger bed shear stresses in one of the distributaries or something like that, that's allowing sediment to be resuspended. But what we see in the structure of the estuary, where here I've put in the salinity contours at 2 PSU intervals, is that all three of these distributaries are partially mixed estuaries. And I will point out that the Pathein distributary, you can see that the distance from the mouth is quite a bit different from the Yangon and the Bogale. And that's because the length of the estuary, the salt intrusion length, is much longer in the Pathein. But I just want to emphasize that we're looking at the same region of the estuary, so the same portion of the estuary, even though it's not physically located in exactly the same region. So even though all three estuaries are partially mixed, we see quite different trends in these suspended sediment concentrations. So I'm just going to emphasize the two sort of bookend members, where the Yangon, we have those really, really high suspended sediment concentrations. It's actually on a different scale than the other two distributaries, so that we can see a little bit of structure to that turbidity. And what we see is that the suspended sediment concentration is actually decreasing upriver. So the upriver does not seem to be the source of this really high turbidity. In the Pathein, in contrast, we see pretty consistently low turbidity, aside from occasional patches where it looks like there's a little bit of resuspension. So what is causing this? Where is this sediment coming from? What is causing this difference in distributary properties? To investigate that, we have to now go back into our tidal-transect data so that we can look at sediment fluxes. So you're now familiar with this type of data. We're looking once again at the Yangon distributary, but now during low flow conditions. And we have a little bit of missing data due to challenges of collecting data in a heavily used port system. But we can calculate that the rough approximate residual sediment flux is still positive, so the distributary is still exporting some sediment. But we see a really significant difference in the structure of the average velocity and bed shear stress during the flooding and ebbing tide, where now the river is not as strong of an opposing force. So now we get peaks in shear stress during both the flood and the ebb tide. We don't have that really long extended period of low shear stress during the flood tide. And so we see high suspended sediment concentrations, really greater than 1 gram per liter throughout the tidal cycle. We're not seeing that pattern of deposition and resuspension. I'll contrast this data with data we collected in the Bogale River during both neap and spring tides. We're showing once again the same data, just in a different distributary now. And you can see that the the residual sediment and water flux is approximately 0. So really that ebb and flood are matched. This distributary is exporting very little water and sediment during the low flow season. You see pretty similar patterns in terms of bed shear stress to what we were just seeing in the Yangon, where we get these peaks in shear stress during both the flooding and the ebb tide. But we see quite a bit of variability between neap and spring tides in terms of the suspended sediment concentration. So during the neap survey, we see this pattern of deposition and resuspension that we're familiar with from the high flow season. But then that signal is really swamped during the spring survey by just really consistently high suspended sediment concentrations. So it seems like just from this data that the tidal forcing is something to do with the turbidity, and that the ocean is likely the source of sediment, since the spring tides are bringing in more of this offshore sediment. And we can dive more into this hypothesis by looking at sediment flux decomposition. So really pinpointing where this sediment is sourced from. This is a relatively common method used in tidal-transect data or tidal-transect surveys to look at where sediment is sourced from, what the dominant processes are in terms of moving sediment, where we can decompose our total residual sediment flux, which is what we have been looking at so far, into 3 components. The first would be a tidally averaged and spatially over the cross-section averaged component. Then we could look at a spatially varying component, but tidally averaged, and then finally a spatially and tidally varying remainder. And for those of you who don't love equations, I have some nice sort of simplified cartoons to give you an idea of what these terms might look like, where this first term that's spatially and tidally average would be that river advection generally. It's usually seaward flux component. This spatially varying but tidally average component would be the estuarine circulation, where we tend to have transport landward at the bed, closer to the bed, and then seaward, closer to the surface. And then we can have really complicated things happening in this final term, where we could have the impact of eddies or resuspension and deposition or morphology, things like that, that are also influencing our sediment flux. So we can look at these terms. We'll start once again with the high flow season when things are pretty simple. So here I'm showing the total sediment flux as a black bar. That's what we have been looking at so far. And then each of the river, estuarine, and tidal components broken down. What we see during the high flow season is not surprising. It's really the river advection, that river export, that's dominating the sediment flux. That's what we would expect. This is a river system that is exporting sediment. So that makes sense. But the interesting piece comes when we look at the low flow season, where there is this difference in distributary transport processes. So now, instead of having the Yangon and the Bogale looking really similar, we have this difference where the Yangon is dominated by this estuarine exchange import term, so this negative term, so sediment coming from the ocean that is imported upstream that's almost balancing that river and tidal component. And we're not seeing as strong of a signal in the Bogale, where it's really more this resuspension and tidal fluxes that are balancing out the river flux. So I'm going to come back to this great figure from Steve Keel's recent paper, where we have this region of intense seabed mixing offshore. And this is really, the offshore processes are contributing to processes within the delta, where when the distributaries are partially mixed estuaries, they will import sediment from offshore if there is offshore sediment available. So in the Yangon distributary over here, we have this huge pool of offshore sediment that can be re-imported into the delta, could possibly be delivered to land surfaces. It's sort of being continually recycled and has a much longer residence time. In contrast to over in the Pathein distributary, where there isn't that same offshore sediment source. And so we're actually seeing a decline in turbidity during the low flow season. So it's really the offshore signal that's defining turbidity during the low flow season. Just to re-emphasize the contrast with the high flow season, during high flow, these distributaries are tidal rivers that are exporting sediment. Somewhere in the upper delta, we're retaining somewhere between 20 and 60% of sediment. And the turbidity is really defined by that upstream delivery. So just to take a moment to summarize this first section of the talk, these individual distributaries of a tide-dominated megadelta are significantly different in terms of both hydrodynamics and sediment transport processes. And so examining just one of these distributaries would actually not have told us as much about the delta as a whole and how the delta operates. However, all told, during a high flow season, somewhere between 20 and 60% of sediment is retained in the upper delta. And we think that this is really due to the relatively low level of alteration to the system. So the floodplain is still relatively connected to the river, and sediment can be deposited on surfaces during that high flow season. And then finally, we can more broadly say that during the low flow season, estuarine processes will import sediment into distributaries if there is offshore sediment available and resuspended. And if you're interested in that concept more, I think Andrea will touch more on those ideas in her talk on Friday. So far I've been talking pretty big picture. Oh, I have one more thing to say about, before I move on to small scale, which is one remaining question that we have. And that's that we're not exactly sure where sediment re-imported into the distributaries during the low flow season, where exactly that sediment is deposited or retained. So this figure is showing quite a bit of data, similar to the estuarine structure figure that I showed, where we're looking at distance from the mouth of the distributary. And the y-axis is the phi grain size distribution of the bed sediment during the high flow in blue and the low flow season in gray. And this is a large splash of data, but really what I want to emphasize is that there aren't really clear trends. There isn't a dramatic fining. There's no clear mud deposition during the low flow season. There's a lot of variability in bed composition in both seasons. And so we'd love to be able to go back and look in more detail at where this sediment is being retained, both sort of across channel and along channel. So that's one final mystery, but what we do think is that some of this sediment is delivered to land surfaces, which is what I'm going to talk about for the remainder of my talk, really looking at these smaller scale processes that are actually delivering sediment to land surfaces, especially within the lower delta, and sort of creating this stable land surface that's so valuable. And for that, we're going to zoom into the center of the delta to this one island, Meinmahla Island, which is a mangrove forest preserve. You can see here, so this is an aerial image of a satellite image of Meinmahla Island. You can see that dark green color, and that's because it is all mangrove forest, whereas this is not really true color, but the land all around the island here is mostly used for agriculture. So the land surface has a really different color compared to this dense mangrove forest. And this island is situated within the Bogale River. So we have sort of an idea of what's going on within the Bogale. Has sort of the sourcing upstream at our tidal transect, and we can use that to look at what is happening within this land surface, both mangrove forested and heavily used for agriculture. I'll also point out that this is a very fun site to visit because it is also a crocodile preserve. There's a large population of saltwater crocodiles that lives in Meinmahla Island, including this friendly beast that we met one day, who's named White Lips by the rangers. It's a 6-meter long crocodile. And then we very nervously got into a 3-meter long canoe to do some field work. So never a dull moment during field work. I love this quote. So this is the environment that we're working in, has been surveyed. When the British were originally colonizing Myanmar, they wanted to use this land as a resource and harvest mangroves. And this was the opinion of the L. Dudley Stamp, who's doing that geological surveying back in 1925, where they say that the most the forest officer could do was to cruise through all the creeks, which would admit a small launch, and to make occasional excursions into the indescribably filthy mud of the forest itself at low tide. And that actually provides a pretty good summary of our data collection methods. We cruise through these tidal creeks in a small launch and make little excursions into the forest itself. Here is Chuck and Aaron about knee-deep in mud with one of the graduate students from Myanmar we worked with, Haley, collecting a sediment core. So we have a really great data set from this island that we collected between 2017 and 2019. You can see we have a wide variety of data and pretty good spatial distribution, and we're still working on processing a lot of this data. And so I'm just going to show you a little bits and pieces, a few of the clearer stories that are coming through and where we're still doing some investigating. So just like with the sort of distributary comparison, we did both long-term monitoring and these intensive surveys. So during the high and low flow seasons, we deployed aqueducts to measure velocity, suspended sediment concentration, and also had salinity sensors on those platforms. We did a lot of surveying of these interior channels, collecting CTD, bed samples, water samples, and photographing banks to look at morphology. And then we also did a fair bit of coring, as I just showed, and we have some absolute land surface elevation measurements with a GPS RTK unit. And today I'm really going to focus on this little inset here, just tell a little portion of the story by focusing on some of these tidal channels. But just to set the scene for this, Meinmahla Island is a really interesting area. It's so if we look very broadly at the delta shoreline, we can sort of break it into two regions that are sort of broadly eroding and broadly accreting. So this is a figure from a really great recent paper by Chen, and you can see that in the western region of the delta, we predominantly have shoreline erosion, whereas in this eastern portion of the delta, we predominantly have accretion. And here is the Meinmahla Island and the Bogale River. And so you can see it is in a region where the coastline is predominantly eroding. But what we see from the island is that the island itself is actually prograding seaward. And so if we look at aerial imagery, we can see from 1975 to 2010, there is this shoal or bank at the front of the island that is slowly rising above sea level, and the island itself is prograding seaward. So clearly there are processes within this island that are retaining sediment and allowing it to aggrade and prograde. And we can demonstrate this further by looking at cores and calculating an accumulation rate for the sediment using lead-210. So this is a core that was collected just from the front of the island in that area where we're seeing those high rates of progradation. And we measure accumulation rates somewhere between 0.8 and 1.6 centimeters per year. So the island is doing a pretty good job of retaining sediment. And we want to really understand how these tidal channels and how this island is acting to retain sediment and maintain this stable land surface. To do that, we've examined two broad types of tidal channels. So this is based on some work that Robin McLaughlin has recently done in the Amazon, looking at tidal channels, where she defined these sort of two categories of low connectivity and high connectivity. And so low connectivity channels are often what we think of when we're measuring sediment flux in channels where there's one connection to the ocean, and then at the other end, the channel dead ends into the forest. And I'll show some data from that. But we can also think about what's happening in channels where there are multiple connections to the ocean, or in this case, the river. And so there are multiple tidal forcings, multiple signals propagating through this channel, and things get a whole lot more complicated. I'll start by just showing some data from a low connectivity channel. Here we are deploying our little aqueduct platform from one of our small canoes that is probably smaller than the average crocodile. So I imagine many of you are familiar with velocity stage diagrams, but I'll just walk through this because it tells a really interesting story. So on the x-axis here, I'm showing the water velocity, where negative is seaward and positive is landward in one of these low connectivity channels. And then on the y-axis, we have water depth, which is changing with the tidal stage. And the points are colored by suspended sediment concentration. So what we can see really clearly here is that the suspended sediment concentration is higher on the flood tide than on the ebb tide, even though the water velocity is higher on the ebb tide. And this is pretty commonly seen in mangrove forests, where we have sediment being transported into the mangrove forest. That fine sediment settles out during high tide, and then ebb tide is not strong enough to resuspend that sediment, and so it is retained on land surfaces. We can actually calculate an approximate net sediment import per tidal cycle, somewhere in the range of 70 to 150 kilograms per meter width per tide. And just to give you an idea of how the scaling on that sediment import, that is about 0.25% of the residual export of the Bogale distributary that we measured during our seasonal surveys, which seems small, but when integrated over the hundreds of channels that are present in the lower delta, is actually a pretty big signal. So this suggests that these low connectivity channels are really efficiently importing sediment and delivering it to land surfaces. If we look at a high connectivity channel, things get much more complicated, as you might expect. And this is where we don't have a nice story. This is sort of like hot off the press. We're still exploring these patterns. What I will point out is that there are multiple tidal signals, multiple peaks in velocity, and there are some really funky patterns in suspended sediment concentration. And we're also getting periods of time where our instrumentation is really buried in sediment as large amounts of sediment pass by. And so this is something that we're still trying to disentangle. So all of what I've just shown is sort of from an Eulerian perspective, looking at a single location and where sediment is fluxing past that location. But we can also think about how this high connectivity channel here that I've outlined our path in red, how processes might vary along the channel. And what we observe is that really at each entrance of this channel, there's sort of what I'd call like a little estuary. where there are significantly different water masses in the island interior than what's in the main stem of the river. And there are these regions where they're mixing, and we get sort of interesting similar estuarine processes, where, for example, if we look at this southern entrance, we see that there is higher salinity near the bed, along with higher turbidity. So we have that turbid ocean water coming in and being imported sort of in similar estuarine processes into this high connectivity channel. And then in the island interior, we have much lower salinity and much lower turbidity. And so we're still sort of examining the structure of this along channel process. But there are these really interesting mixing and import processes happening at both entrances to the high connectivity channel. The last thing that I will say about this island data is that there's also a significant groundwater signal. And so I'm including this because I think there are some more chemically focused, biochem focused people here who might be interested in thinking more about what sort of signal groundwater can contribute to flow. And we see that there is significant groundwater flow. And so to illustrate this, I'm just showing some water level data. The blue is the water level in the main stem of the Bogale River. And I'm showing both the low flow northeast monsoon and the high flow southwest monsoon for a spring neap cycle during each of those time periods. And during both of those seasons, we had a little well deployed within the island, so we could measure the water table within the island. And so that's what I've plotted in black. So if we start with the high flow season, we can see that the forest is inundated as we'd expect. This is a mangrove forest. It's inundated at high tide, and during the spring tide and during the neap tide, the water level within that forest never drops down as low as the river water drops. So there's always water flowing out of the ground and back into the river, and then sort of being pumped in again at the next high tide. So we know that there's a lot of exchange and water retention during the high flow season. During the low flow season, there is a slight difference. So this is the much drier season. And what we see is that during spring tide, we have that same constant water table that's pretty high. But then during the neap tide, that water table drops, and it actually drops below where our instrument could measure it. And then gradually the groundwater is replenished during the onset of the next set of spring tides until we get back to that spring tide pattern. So there's quite a bit of exchange between groundwater and the river, and we're still sort of disentangling how that signal might be impacting our tidal channels. I think we often think about tidal channels as sort of these impermeable surfaces where it's just water flowing through, and then when the water level exceeds the level of the flats, water can pour out onto the flats, and sort of we don't really consider as much how flow might be transporting through the ground as well. So that'll be really interesting, and stay tuned for more. So just to bring this section to a close, there are lots of little loose ends, but overall what we know is that this island is aggrading, it's accumulating sediment, and it's prograding seaward. And we know that the low connectivity or dead end channels can pretty efficiently import sediment, which is probably contributing to this island stability. Whereas in the high connectivity channels, things are complicated, and we're still sort of disentangling signals and trying to figure out what the role of groundwater flow is. And then I will give one more plug for Andrea's talk, which is that we can also compare what happens when mangrove forest is replaced with agricultural fields. And I think Andrea will touch on that and the role of human impacts in sediment transport. And with that, I'm going to wrap up and say, once again, thank you to all of our wonderful collaborators. I really feel very fortunate to be part of such a wonderful research group, and I feel like I've learned so much from all the people I work with. And with that, I'd love to take questions. Thank you.
And thank you so much for this wonderful talk. So let's see, let me open. So now the audience, you are able to unmute yourself. If you have any question, say Steve, raise a hand. Steve, go ahead.
Hey, Anna, nice
Hi,
talk. I really enjoyed hearing about your work, and I think it's, you know, answering a lot of questions and also bringing up some new questions. And so I don't know if this is a question or a comment, but just we've been working. I have a master's student who's finishing up, Evan Flynn, and she's been working on the centennial scale shelf budget. And what's interesting is that you know, if we compare it with Paul's Holocene budget, it's about double, which is not unexpected, but it's also about at its upper end anyway. It's about equal to the Barones estimate. So when I saw your 60% retention on the Delta plain, so either that's a bit high or the Barones estimate is too low, or the offshore part is, you know, we're wrong. But I think trying to balance all the different budgets is challenging. But to sort of, maybe this is the question part. I wanted to let you know what we were up to.
Yeah.
But that preserve, is that representative of the rest of the Delta Plain in the mouths of the Ayeyarwady area? I mean, you guys have visited there. I haven't been there, but I'm wondering if the rates that you're seeing there, clearly you're seeing high retention there. Is that, you think it's reasonable to extrapolate from that area? I know you haven't done that, but.
Yeah, so I just want to go back first and say that I do have a huge range of estimates for sediment retention within the upper delta.
Yeah.
And I think that the amount of sediment being deposited offshore says something about the residence time, where I think that there's a lot of sediment being sort of exchanged with the delta. It's not really this sort of linear sediment from the main stem is delivered to the offshore, but it seems like it's sediment is retained on the floodplains for a while and then perhaps resuspended or moved seaward, or sediment from offshore is then re-imported and things like that. I think there's some interesting stories there that maybe we won't get to answer in the near future. But yeah, in terms of whether, I don't think that Meinmahla is representative of the entire delta, because it is a mangrove forest preserve. But there are still large tracts of mangroves and a lot of these little tidal channels. And I would also say that the Ayeyarwady Delta is keeping pace with sea level slightly better than neighboring deltas, where there is more infrastructure, more levee development especially. And I think that is a function of this efficient sediment import and delivery to land surfaces.
Yeah, that was another thing that I don't want to take up all the time, but you know, when you talk about import into the Yangon, it's probably a combination of Ayeyarwady, Sitang, and Thanlwin sediment, because that whole bay there is a big washing machine, and the stuff is just homogenized. We see that in the sort of the geochemical signatures offshore.
Yeah.
Yeah. So anyway, thank you. I'll let somebody else speak.
Thanks, Steve.
So Hannah, I have a quick question. So in your first part 1, you show very nicely, during the low flow, that for example, the Yangon River, during the low flow, there's a big portion from the river estuary portion, from the sea into the river. And you compare the nip and the spring tide. Did you any data show during the flooding and ebb? This is a daily difference. During the flooding, how much the big peak, or during the ebb, when they flow to ocean, any difference?
In terms of comparing the spring and neap flood and ebbs, you mean?
Yeah, because you show the spring and the neap, that's no big difference. But how about during flooding and the ebb, during the big push in and flush out?
Yeah, so there is during that's where like it gets really, it's hard to show all of this data because I end up saying like high flow, low flow, spring, ebb, flood, or sorry, spring, neap, flood, ebb. But there is more asymmetry between the flood and the ebb during the high flow season because that river is such a strong force.
Yeah.
So you have these like really, really asymmetric tides, whereas during the low flow season, they're actually relatively symmetric because the river forcing is so much weaker. And so we have, there's sort of similar water being transported, but the suspended sediment concentration is significantly different because there is this offshore pool that's sort of like sloshing back and forth, at least in the Yangon. I'm not sure if that answered your question.
Yeah, I mean, during the low flow in the both of the Yangon and the Pathein, maybe most of the flow mud from the ocean and actually inside the estuary, just back and forth is still hanging there. So during the low flow. But anyway.
Yeah.
Okay.
I think there is a lot of that sort of just like, yeah, as Steve said, washing machine. The sediment is not really like depositing per se, it's just sort of being fluxed through continuously.
That's true. Okay, we have some questions. So I know Dustin is unmuted. Do you have a question? If not, I give Bob. Okay, Bob, go ahead.
Very, very interesting talk. So I see my video is not on. Just give me a second here. Okay. I'm wondering where you would say you should go if you would like to get the terrestrial end member of a river in this system. In other words, suppose you wanted to know what the organic matter signal was coming from land, and you have a mix of sediments that have been imported from the ocean, and obviously it's carrying, as Steve mentioned, a variety of tracers, including organic matter and radiochemical tracers from the ocean back up into the distributaries. So where do you think you have to sample if you wanted to get an end member?
That's a good question. So certainly tides are not propagating. The tidal signal is sort of decaying out. It doesn't really reach much past, I don't even know if it does reach to the apex of the delta where all the distributaries are branching off. So I think somewhere in that reach, there is sort of a more, at least in morphology, it looks much more fluvial. Within that region that I very broadly classified as the upper delta, which is basically just upstream of where we were able to sample. And so I think somewhere in that continuum, you'd get a really nice signal, and that you could then sort of see that transition into the zone where we were working, which was very marine influenced. So I think you still could do that sort of within distributaries. I don't think you need to go back all the way to the main stem. But that would be really interesting. I feel like there are so many questions that I'd love to answer both longitudinally and latitudinally across the delta. We'll see if that ever happens.
Thank you.
Yeah.
Okay, anybody, any question, any comments? Oh, Michael, Courtney, so.
Yeah, actually following up on that upper and lower delta, you know, in Bangladesh, Carol Wilson showed that there's a really prominent break in topographic slope between the upper fluvial and the lower tidal delta. Is there anything, you know, similar? I know you drew that boundary just upstream of where you were working, but is there, have you looked at the topography to see if there is some kind of topographic break that might correspond to that boundary?
Yeah, I'm trying to, so the Chen 2020 paper has a little bit of that sort of longitudinal data. And I don't remember a really distinct break, but I could be misremembering. The difference in morphology is really a matter of channel sinuosity. There's a region between the apex of the delta and our sort of study region, where there's really high sinuosity and it seems very fluvial, and there are sort of more like braided sections. Trying to think of all the features that we've spent a lot of time just on Google Earth, sort of zooming around and looking at these different regions of the river that are clearly influenced by different factors, but we don't really have ground data.
Yeah, because the sinuosity also changes in Bangladesh. You may be able to put everything together to better define that boundary.
Yeah, and I think that's a piece that Evan Lahr, who's another grad student in my lab, has sort of been dealing with more. He's doing more of the like remote sensing and trying to create some algorithms to trace channels so that we can calculate those things sort of on a delta scale. So stay tuned.
Okay.
Michael, which pagoda in your background?
That's at Kalewa on the Chindwin River.
Oh, Chimwin River.
Yeah, so way upstream.
Okay, good. Okay, and then Courtney.
Hi, great talk. I really enjoyed it and learned a lot. It was great to see what you've been doing with your hard-earned data. So as you might know, our group has been working on a numerical model of where that stuff goes once it gets into the coastal ocean. And we feel like one of the biggest uncertainties in our model is specifying the sediment loads coming out of the rivers and also the properties, like how much is fine-grained, and if it's fine-grained, how much would be flocculated. Right. So do you have some broad brush advice for us in terms of those two things?
That's a great question. We do have some data on flock size, so we're happy to, I can talk to you about that more. We haven't really processed much of it, but we do have some settling chamber data from within the distributaries, so we could at least give you an idea of that within the distributaries. In terms of which distributaries are carrying the missing portion, so I guess I'll pull up a figure. That was something that I really wanted to answer, but we just didn't quite have enough data to calculate all the things that we would need to be able to calculate. So
do you think satellite data would be a helpful way to go to answer that? Or
so there was a new paper from Meinmahla, I keep butchering his last name, where he was calculating partitioning based on how like funnel shaped, based on morphology basically. And so I really wanted to be able to do that, but in order to do that, we would need better bathymetry data within the distributaries. And that's really the piece, like we don't have water depth. It's really the piece. Like my gut instinct is that it is these wider distributaries over here. Like, so this one that my mouse is over is the Ayeyarwady distributary. And I actually can't remember what this one next door, but I would guess that those are the two other big players, and that this one is less of a player, but it's really hard to tell.
And it's mostly fine-grained, all fine-grained, and then flock characteristics. Do you think they vary over spring neap cycles or high season, low season?
I do have some published data on disaggregated grain size, which shifts a little bit from season to season. They're just between whether it's clay dominated or silt dominated. But I haven't really looked very much at the flock data. I feel like if I had to guess off the top of my head, I would say that maybe the flocks are a little bit bigger when it's estuarine, but we certainly were seeing flocks during the high flow season when it was purely a tidal river. Maybe Andrea has a better memory of looking through that camera.
Yeah, I mean, I certainly stared at them a lot, but it was kind of, it's not the best flock data that we have, but I think I'm going to agree with Hannah that it seemed like they were slightly bigger during the low flow season when we had estuarine conditions right there within our study reach. But they were never huge flocks and so more micro flock sized. And we'd have to look at it more for sort of more detail, but we're happy to do that. We just haven't focused on it because it wasn't the finest data stream that we've ever had or the best quality data stream.
We may end up running sensitivity tests with a range of sizes and then see how important it is to the dispersal.
Yeah.
Thank you. So I really enjoyed your talk. Thanks.
Oh, good. Thank you.
Courtney, when you met already your model, maybe you should also, both of you come here, talk about the model result. Courtney.
Come to this seminar or come to North Carolina?
No, I know everybody gets a Zoom fatigue, but I hope I invite you in person, but let's see. Okay. Hannah, so, when Daniel worked on the Mekong project, finally he came out to some budget, how much the river discharge budget. Do you think you guys were able to give a rough estimate? Because, Cambridge, Cambridge group, they just come out some number based on ADCP, but they work a little bit upper in the delta apex, but you working more on the, estuary tidal portion channel. Are you able to do something to come out something?
So I think we could do some budget that would have like pretty big air bounds for the distributaries that we have, considering that, we have pretty sparse measurements. It's hard to extrapolate from like one neap tide and one spring tide during each season. But then like the big mystery in terms of total budget for the river is those missing distributaries. Yeah.
And also the challenge question, like Courtney asked, how much each individual distributary able to discharge during the different season. I mean, of course, that's very challenging. And like the chain, you talk about the chain 2022 paper, we try to do something, but still, based on morphology, they already get a rough idea. But based on tectonic analysis, one background I want to provide, in the western part of the delta, overall the long-term uplifting rate is about 1 meter per 1,000 years. Okay. 1 meter per 1,000 years. That means during the Holocene, they could be uplifted about 6, 7 to 10 meters. This is somehow explained the river overall gradually shifting from west to the east, now heading more to Yangon or even the top portion of the Gulf Mataband, gradually shifting to the east. Just like a Ganges-Brahmaputra. I think the Ayeyarwady system kind of following the step of the Ganges, gradually shifting from the west to the heading to the east. But anyway, that's very interesting. Any more comments or questions? Hannah, you can treat this recorded warning as your PhD defense. I think you passed your wonderful talk. Great.
I'll tell Andrea and my committee that.
No more defense. This is so great. I think looking forward, again, Friday, same time, 10 a.m. East Coast and 7 a.m. Pacific time. So this Friday, we're looking forward to the Andrea's talk. So, okay, Hannah, thank you very much in this personal difficulty time, and you still managed to give a wonderful talk. I think this is great. Thank you. Yeah.
Thank you, Paul. Yeah, thank you for inviting me.
Very happy. That's a great discussion. Thank you. So I'll see you Friday. Okay.